Okay, welcome back. So we have been doing some wonderful work talking about continuity at a point. And if you have been paying particular attention, we've also been talking about continuity at a point from one direction and two directions. And there is a difference. So when I started with a one direction continuity idea, and then when we went to the definition of continuity, it was a two-sided limit continuity. And let me explain this. So if I'm looking at continuity, of f of x at x equals a from the left, then what I'm talking about is this changes. And I hope you understand that. This is now a very different saying than continuity from the left and the right. This would just be continuity from the left, and it would be something like this. So there's the limit. The left-handed limit exists. Yay! And then if it's going to equal, there's it being equal, the f of a being defined for some value. Yay! And the fact that they're equal to each other means that they are continuous. Yay! Whereas this would have condition 1 being satisfied. The left-hand limit does exist. And this would have the function is defined at f of a. Yay! But the third condition doesn't exist, and that would be discontinuous. But do understand that you would have to always say discontinuous at a from the left. You would always have to be very cognizant of what you're saying. When we go to say something like this is a much bigger statement. Oh my goodness, that's such a bigger statement, because that's talking now about from the left and the right. So condition 1, for it to be true, that has to look something like that, or something around that range. For condition 2 to be true, I've got to have it defined at some point. And for condition 3 to be true, well, right now it's not true, but if I pick it up and move it to there, now condition 3 is true. And that's continuous at a in both directions, which is why this is a very different statement than that. And all that changes with that little negative at the top of it. And that was it. So pay attention. Don't miss anything. Very important stuff. Okay, so now I want to go from talking about continuous at a point to continuous on an interval. Because look at this. This is f of x. And we're only talking about the continuity at this point. What about the continuity everywhere else? Well, if you look at it, the graph says it's continuous everywhere else. So it's really not a deal, but we should start talking about that. We shouldn't just be talking about a particular point. We should be interested in the function in general. Where is it continuous? Where is it not continuous? We've sort of touched on this a little bit already. You know certain functions. You've grown up in grade 10 knowing all about y equals x squared. That's pretty continuous. You didn't jump in gaps or anything there. That's a continuous function. And you've grown up in grade 9 drawing lines. Lines are pretty darn continuous. There's no jumps or gaps. And last year you did some of these guys. You had Mrs. Manchi, I think she calls that the wiggle. And we've got the cubic function going there, right? And that is continuous. And then last year you also did some fun stuff. That is continuous. What do all of these have in common? They're all polynomial functions. All of these are polynomial functions, and polynomial functions are continuous everywhere. Okay? We have some other functions that are interesting that we're going to talk about. We have power functions. We're going to have some power. Here's a power function. Now, that's not continuous everywhere. It's not continuous where it's not defined. It only starts being continuous on the right-hand side of A in this particular example, but it's continuous everywhere it's defined, isn't it? And that's what we say. We say that that type of function is continuous everywhere it's defined. And we have rational functions. Those are functions h of x, which is built from an f of x over a g of x. So rational functions now. Rational functions are great, and they're continuous. If they're made up of a polynomial on top and a polynomial on the bottom, they're continuous everywhere except where the bottom equals 0. Now, you're not used to seeing me say equals. You're used to me saying g of x can never equal 0. But I'm talking in the reverse now. I'm looking for places where it would be discontinuous, and that would be anywhere that it does equal 0. That's going to be a place that's discontinuous. And that's an infinite discontinuity, right? That's one of those asymptotes, those vertical asymptotes that's going to show up. So something to keep in mind is, when is a function going to be continuous and discontinuous, and where can it not be continuous or discontinuous? And you've already seen a lovely example, 2 examples like this, that if I have a addition of 2 functions, and if this is a polynomial, it might be continuous everywhere, and this is a polynomial, and it might be continuous everywhere, but you know what? They might not be continuous where they meet. In which case, the only place that I'm really interested in this one is where they're meeting, because if I know that this is the type of function that's defined everywhere on its domain, and I know this is defined everywhere on its domain, then I know they're going to be continuous everywhere. Okay, so now that's our concepts. Let's do some mathematical definitions. So we're going to say continuity on an interval. Yes, absolutely. Thank you for that. So we're going to do continuity on an interval. And this is in contrast to not a single point anymore. We good? More? There we go. That's fine. You guys let me know if you can't see it. Because if my studio audience can't see it, I'm pretty sure the kids at home can't see it. Excuse me. So, if a function, this is a definition, if a function is continuous, can I use C-O-N-T with a dot to stand for continuous? Yeah. All right. If a function is continuous for all x values in an interval, and we're going to call that interval I. I'm doing formal math speak, because you know what? You're going to be going into programs where you're going to have to be able to read formal math. That's one of the reasons why I'm having you write out these notes rather than just photocopy them and give them to you. So on an interval I, what we're going to say is, we say f of x is continuous on the interval, and we don't even say the interval. We say what the interval is. So if I know that a function is continuous on an interval I, what we say is that f is continuous on I. It makes it kind of simple. And if a function is continuous on an interval negative infinity to infinity, in other words, everywhere, that's kind of what we say. We say f of x is continuous everywhere. And if you haven't noticed, mathematicians are really lazy. We even shorten this down. We say f is continuous. We don't even put in the everywhere. So if anyone ever tells you, hey, they say, hey, I'm a function and I'm continuous, that's a pretty important statement. That means he's continuous everywhere. Okay? So that's pretty neat. Things that we have to remember, and I think we've just talked about this, and this is the most important one, is that polynomials are continuous everywhere. Everywhere. And in fact, if I wanted to write this even more, I would just say polynomials are simply continuous. Bottom line. And rational functions. That's the other one that you should know. Rational functions made up of polynomial functions. So h of x equals f of x over g of x. They're going to be continuous everywhere. They're going to be continuous everywhere that g of x does not equal 0. And those are the most important that we're going to talk about. What about if I have functions and I make a a new function out of them? Well, if both f and g are continuous functions, then I'm going to say on an interval I. So what I'm saying here is that f and g are both continuous on the same interval I. Then the following are also continuous on I. And that would be any sum or difference of the two functions. That would be any multiple of the two functions. And that would be any division of the two functions or quotient of the two functions. And again, as long as g never equals 0 for any x on the I. And I threw this in here just because I want you to start to be able to read it. This says for any x value, so for any x value on the interval I. That's what that says, and you need to be able to start reading it. So I threw it in there just so I can start doing that to you so you can read what that says. I'm going to pause the video there and I'll be right back.